Let's talk about internal resistance. So this subject brings up a lot of external resistance into students because a lot of students just really struggle with this from my experience. And hopefully by the end of the video, I'm going to be able to show you that it's actually a really simple concept. So these are the two main formulas you'll see on your formula sheet that are given. And they're essentially the same thing, but they're used in different ways. And yeah, so these are the formulas you'll be using on your formula sheet. And we'll probably look into these in more depth at another video and also a later stage in this video. So let's get into it. First, let's talk about EMF. So let's look at the definition of EMF. So it says the total energy supplied per coulomb of charge by the cell. So I want us to underline this. Total energy. So the EMF says, what is the total energy that can be supplied to the circuit? Is essentially what this definition is saying. So EMF stands for electromotive force. So it tells us what force or what energy can we supply to the circuit. So what I like to explain to students is this. A 10-volt battery is a 10-volt battery. So no matter what happens, if a battery has an EMF of 10 volts, and it means it can supply 10 volts, it will always be 10 volts. And I know you're thinking, or you have some thoughts at the back of your mind, but sometimes it changes, sometimes it becomes this. I know, I get you, but it's really important to realize that a 10-volt battery is always a 10-volt battery. We'll look into what changes that makes it seem like it's not a 10-volt battery. And let's talk exactly about that. A 10-volt battery is a 10-volt battery. So it always supplies a total energy of 10 volts. It supplies this energy of 10 volts, but it may not always effectively apply that 10 volts. And that's because we have internal resistance. So this is the resistance inside of the battery that takes away from this 10 volts. So this internal resistance will take away from this 10 volts, which is our EMF. So the EMF is constant. Our EMF is always constant, but what happens is the internal resistance takes away from this effective supply. So it's often what people call lost volts. So it's what's called lost volts. Let's look into that in more detail. So we have the circuit here. We have the cell over here, and it supplies an EMF of 10 volts. So the EMF is 10 volts. And remember, this EMF is constant. So this 10 volts is constant. We have this little r, which is our internal resistance. So I know this might look a bit different to what you're used to seeing with internal resistance, but just stick with me, and I think this diagram will be quite helpful in explaining internal resistance. We have this internal resistance, R, little r, is 1 ohm. Then we have this external resistance of 4 ohms. So the reason it's called as R external is because this R is our internal resistance. So we could also write that this was, we normally just write little r, but we could also write that this was the internal resistance. Okay, so let's say we have the circuit going for us, and we know that the internal resistance, the current is 2 amperes rather. So we have everything we need to use Ohm's law, which says that voltage is equal to I times R. So this is what Ohm's law tells us. So we can work out the voltage across this resistor over here. We can work out the voltage across this. All right, so if we do use Ohm's law, we'll find that it's our current of 2 times our resistance of 1. So this is 2 volts. This resistor is 2 volts. Then if we do the same thing over here, we get a voltage across this is our current of 2 times our resistance of 4. So this is 8 volts. All right, so what essentially happens is, because we have a current going through the circuit, whenever we have a current, we're going to be having these lost volts, because this related over here with our internal resistance, these are essentially what some people call lost volts, because we have this EMF of 10, but this internal resistance is taking away. So this 2 volts is taken away from this 10. So that 10 actually gets reduced by this 2. And we can see that because there's actually only this available. You see how there's one resistor and it's using all of the available energy that's left over. It's using the voltage across this is the only thing that's left. Because as I said before, this 2 volts is taking away from our EMF. So what's actually available is this over here, this V load. And this is our V load over here. So the V load shows us the total voltage that's available after we account for this internal resistance, because this is our V internal. And some people call it V lost. So it's OR. So this means V internal or V lost. So you can see that the circuit can actually only provide 8 volts because these 2 volts are taken away from the EMF. There's like a cost. You can almost think about it as it's almost like a tax. It's almost like how the government takes a tax from your salary. So you get paid this 10 volts, but there's this tax of 2 volts. So what's actually only available are these 8 volts. So if you look at this equation over here, this EMF, the second one over here, so equation 2, you can see that the V load is actually what's available. And this V internal actually takes away from the EMF. So another way you can write this equation is you can say V load is equal to the EMF minus V internal. So the V load is actually what is available. So it says what is available. So you can almost think of this after taxes, what's available. So that was a discussion on what internal resistance is, but let's look at a deeper analysis of this equation, these two equations. So these two equations are actually the same. They're just written in a different format because you'll see that V is equal to IR. This is from Ohm's law over here. And if I expand this first equation, so this is equation 1, if I expand it and I distribute that I get this. IR external plus IR, little r. But this I external is actually just, this I external just becomes V load. And this IR is actually just our V internal. So you see how these equations are actually the same, but we can use them in different ways. One thing I just want to point out and discuss here is this term over here, this R external. So what you normally see is you often have a diagram drawn like this, where you have the battery, so in this case it's a cell rather, an internal resistance, and you have this green box around it. So this green box is saying you have to do this calculation here. So you have to work out your V load, because the V load again is going to be if you minus the EMF from this V internal. So let me write this here. This R is going to be giving you a V internal. So to work out what comes out of here, you actually have to take, I'll write it here in green, you have to take that, what comes out of here is your V load. So the V load is just going to be equal to your EMF minus your V int. So that's why sometimes I have this green box. So I wanted to show you that, but also, as I said, I want to be discussing this R external. So the R external means your external resistance. So this little r is not external resistance because this is the little r over here. And you can see it's separate from our external resistance. So that's the internal resistance related over here. That's why it's in the box. But our external resistors are here. It's R1 and R2. These are our external resistors. But often what we have to do in these internal resistance questions is we have to be very careful how we work out this R external, the resistance rather. So if we look here, we actually have to combine R1 and R2 to get an effective resistance. So we need to combine these two to get a combined effective resistance. And these two resistors are just in parallel. So we can just use our normal resistors in parallel laws. We just get this. That's not going to be an equal sign. Plus 1 over R2. So when we solve this, we're going to go through the motions and we're eventually going to get that R parallels equal to something. Let's just say in this case it's 4 ohm. So this R parallel, when we combine these two, what we're going to get, if I do a quick resketch of this, it's going to be very quick, so it's going to be very messy. But if I just do this, as I said, it was going to be messy. if we do this thing over here is now our R external because we've combined the two. So we need to be very careful how we combine these two resistors. So I hope this discussion makes internal resistance a bit clearer for you. And again, I just want to highlight that a 10-volt battery is a 10-volt battery. So if it's 10 volts, its EMF will always be 10. And we can see, well, rather we should remember an important fact. I'll put it on the next slide for us. An important fact we need to remember is that the V load is equal to the EMF. When, very important, this is only when, I'll put in red, when current is equal to 0. Because we have that the internal resistance, so V internal, is equal to current times little r. So if we look at this equation a bit clearer, we can see that when I is 0, like we have here, so when I is 0, let me fix that. So if we put a 0 in here, you can see our internal resistance will be 0. So that's when we have this case over here, case 1. But what happens when we start increasing this current? So when we start increasing this current, this V internal will also increase because our R this stays constant. So we have that current is directly proportional to your interior volts. Also, this is also sometimes known as your loss volts. So the amount of energy, the voltage that can be supplied, decreases when our current increases, because this formula over here is only valid when I is equal to 0. But what we normally have is this. V load is equal to EMF minus your V internal. But we know that current is proportional to V internal. So you can see that when the current increases, this will increase. So let me actually do this in another color. This V internal will increase. And when V internal increases, remember our EMF is constant. 10-volt battery is a 10-volt battery. So if we're subtracting a bigger number, you can see how our V load has to decrease. So we have that the load voltage, or what we actually have. Remember, the voltage, the V load is what we can do work with. So it's what the energy we actually have left with when the battery is taken away its energy. So we have that the V load is actually inversely proportional to the interior voltage. So when our interior voltage increases, our V load will decrease, as I've shown here. This is an important thing to remember. And the reason is, if we draw another diagram over here, and I'm going to put that box around it, because remember this box, anything that comes out of this box is actually usable. So you'll see that this is R and this is our EMF. But remember that the voltage across this is going to be given by voltage is equal to the current in the circuit times R. But what we have to do is to work out what actually comes out of this green box. We have to take our EMF minus this V internal. So remember this, what comes out of this is our V load. So whatever comes out of this is our V load. All right, so I hope that was helpful. And again, I hope that this makes internal resistance a bit clearer for you, because I know it is a massive area of confusion for students. And if you guys have any more questions or want me to go into deeper, some more depth in some of these concepts and look at them in a bit more detail, feel free to let me know. Hope this helped, as always.